Today we're going to be looking at creating a 3-point bend in Abaqus. I'm using this pin to apply a load and then showing you how to extract the load and displacement data to develop that curve. To simplify this particular example, I'm going to be using a boundary constraint to define the support pins on the exterior of the specimen, and then we're going to be initiating a contact constraint between the pin and the surface of the specimen, just so that the specimen deforms correctly around the pin. So to start with, I have two parts prepared already. So I've this thing which I'm calling a laminate. It's just a rectangle and it's partitioned. These partitions are important for the boundary conditions that are going to be applied. And then the second part is a pin. I made something very similar in an earlier tutorial, so we can see as well that I have a mesh applied to both of these parts already. Okay, so now we have to assemble them and create the contact constraints and put all the boundary conditions on. So I'll just double click on instances. Going to bring in the laminate and then that and just offset it. Now I have to put these in the correct locations, so I'm just going to go to constraint and edge to edge. I'll select that edge and that. I'll just flip the direction. Okay. I'm actually going to delete that edge because it's flipped to the wrong side of it. Okay, so try that again. Constraint, edge to edge, that, and try the default. Okay, that's fine. And now use face to face. So I'll just select that face and that. Make sure they're pointed the right direction. Set the distance apart at 0. Okay, so now it's just positioned correctly. I've yet to apply the boundary conditions. I think I will do those next. So go down to boundary conditions. The first one, make it a displacement and rotation. And I'm going to put that one here and here as well. I'm not going to create a set, so just accept that. Okay, actually I still have to make the step. So double click on steps, continue, and I'm just going to accept all the default things there. So now boundary conditions. Again, same settings, and just select these lines. And this one I'm going to limit in the U3 direction. So that's the Z direction, so that's the direction that the pin is going to be pushing in. So I don't want to allow my specimen to be to be pushed in that direction at these points. But it's allowed to slide across the X or the Y, okay? So we'll just accept that. The next boundary condition then will be, okay, so I'm just going to select around here. And this is going to be used to stop the laminate moving in the Y direction, just along this line. So it means that it can expand because of Poisson's effect during loading, but it won't slip out entirely from the loading situation. Okay, so we'll just apply that, and that's in the U2 direction, so limit that to 0. And then the third boundary condition. Okay, so I've one boundary condition applied in the Z, this one is applied in the Y, and now I need a boundary condition in the X. So I'm just going to select the center line here and limit that in the X direction. So it can still move in the Y due to this pin pressing on it, and it can move in the Z due to the pin pressing on it, and it can still move in the Y because of Poisson's effects. So I'll accept that. The fourth boundary condition then, I'm going to put that on the center pin. And I'm just going to limit that in every direction except for the loading direction. So X and Y be equal to 0, okay. And okay, now I have to put in a reference point. Okay, so go back to the assembly and use this tool and select to create an offset datum point. I'll just select the back point here and offset it. I offset it in the minus Z direction by whatever you think is an appropriate length, considering the scaling of the rest of your model. So it's created this datum point out here, and I'm going to make this a reference point. Okay. So essentially what I'm going to do here is define a relationship between that point and the base of the loading pin. So basically if you tell that point to move 3.5 millimeters in this direction, the loading pin will do the exact same. And I can extract load displacement data from this. So it'll tell me the force that manifests itself on this pin as I'm loading by that certain displacement. And it's just a neat way of doing it. So I've this put in place. The next thing then I will do is define the... Okay, so I have to make sets. I have to turn this into a set, and I have to turn the bottom of the pin into a set. So under the assembly module here, just double click sets, and I'll call the first set the pull PT, just PT for point, and select that reference point. And then another set, we'll call it pull face, and that'll be just all of this face down here. Okay, so I've my two different sets there, the pull face and the pull point. So now I have to define the relationship between them. So go into interaction and click on the create constraint button, and we'll go down to equation. It's the way that I found it's easiest to define this relationship. Okay. So if you just type in -1 here and 1 here, this basically means, okay, well first I'll put in the pull face and then the pull point, and just put in 3 for degree of freedom. So basically what the -1 and the 1 define here is that everything that the pull point does, the pull face will do the exact same. If you had 1 and 1, the pull point and pull face would be doing the opposite thing, or inverted. So just accept that as it is. So we've defined that relationship. I'm going to now put one more boundary condition in there. And I'll just call this one displacement. and I'm going to apply it to the reference point. And this will be in the Z direction, and I want my displacement to be 3.5 millimeters, so that's 0.0035 meters. So we'll accept that. And the next thing I will do is just to define the contact between the pin and the laminate or the other specimen. So back into the interaction module, I'm going to create an interaction, surface to surface contact. So it's asking me to select the master surface, and the master surface is always the harder surface. So that'll be the pin in this case, because I've made the pin stronger than the specimen. Or at least it's stiffer, it has a higher Young's modulus. So we'll accept that. And now it says choose the slave type. We'll make it a surface. And just select the regions of the surface that are in contact with the pin. Okay. So accept that then. Now we have to define the contact. So go down to this box here which says contact interaction property. Click on the create interaction property button. And just continue. So we'll just define, okay, the tangential behavior, we'll just take the default which is frictionless, and the normal behavior we will just accept that as being hard contact. Okay. We will click on automatically smooth 3D geometry surfaces where applicable for the moment as well. Okay, so that's the contact defined now as well. I'm just trying to see if there's anything I've forgotten before I go and try and run this analysis. Okay, so I want to get load and displacement data from this point, which is representative of the pin. So I'm just going to set up that data now. We'll go to the output here and edit it. Okay, so I don't want to get energies out. In the history output I want to get forces. No, okay. I create a new history output from step 1. Okay. So I want it from a set, and I want the set to be the pull point. So because I just want to get the data from that point. The force will be the reaction force in the Z direction, and I want to get the displacements, so the U's, translations and displacements are the same, and in the Z direction again. So we'll accept that. And as far as I can tell, I think of everything set up and ready to go, so we'll just create the job. I'll accept that. Okay, and then submit it and see if it works out. So it says here that the job has been completed, so view it, go to results, and click on the contour plot. Okay, and now we can see that it's successfully bent the specimen. There are no stress concentrations here and here, just highlighting the fact that the pin was allowed to slide over the boundary conditions that we had set up there. And you can see here the high stresses on this side and this side. So that's the compressive stresses on this side and the tensile stresses. There's a very abrupt gradient here between the three elements simply because there aren't enough. We should have more elements there and give us a smoother gradient between the tensile and compressive side. But that's just showing how the contact modeling should work. The next thing is that we want to extract the data from that reference point that I have back here to plot the load against the displacement. So we'll go to XY data, and it's from the history output. And okay, this is the reaction force on the pull point, so we'll save that as force. And then the displacement, save that as displacement. Okay, so we'll dismiss that, and now we want to, okay, at the moment this is displacement against time, so we want to plot the displacement against the force. So, okay, double click data, and go to operate on XY data. And we're going to, these are our two things, the force and displacement, so we're going to combine those onto one graph. So click on the combine button. Displacement is our X, double click that, and force is our Y. So plot the expression. And then you can see here our force against displacement graph for the particular loading situation that we encountered earlier. So we can go back into to look at the contour plot, and we can animate this as well. So click on the animate options. Frames, we will make it 50 frames just because to make the animation smoother. And we'll just say full cycle, apply that, and click on this to watch the animation. So you can use that in presentations as well, could be quite useful. Okay, that's all for today. I hope some of it was useful. Thank you.